All right, new unit in calculus is going to be all about particle motion. For Calc 1 purposes, we're going to focus on what happens when you move along a straight line. So sometimes called rectilinear motion, particle motion, you can think about an object in motion, all those different things. Here's Mr. Lakin and I racing. Your concepts that will be assessed, we're going to do a lot today, but this is just your intro video. We continue to work on these next things for the next couple of lessons. So right now it's just kind of an intro, get your head wrapped around the information, and then we'll continue to practice, but we're kind of introducing a lot of vocabulary today. Particle motion notes day 1. So when we talk about a particle or somebody moving along a line, okay, you can think about a person instead of a particle, but often we talk about a particle, we reference their position as S of t, sometimes referred to as x of t is another way you'll see that written, and that represents your position on a graph. So when we talk about linear motion, okay, I'm going to pull up, I have this guy here, moving man. So I'm going to create a scenario. Here's moving man. He's starting at 0. This is going to be considered his start point, all right? And moving man is going to move towards the house at 4, turn around till -2, and then go back to where he started. So if we think about moving man, here he is, goes towards his house 4 meters, turns back around, -2 meters, back to where he started. If we were to graph that on a line, we could say this was his start point. He moved 1, 2, 3, 4 meters to the right. Then he moved 2 meters back and then ended up where he started. So if we were to trace his path along a line, we would start here, we'd go 4, back to 2, back to 0. And you wouldn't actually see his change, right? Because you're just drawing over itself. So what I'm going to do to accentuate that is to say, okay, I'm going to go 4 meters here, I'm going to turn back around, and then I'm going to end up right here. So if we think about his displacement, meaning his change in position, okay, his displacement is actually equal to 0, right? He ended right where he started. But his total distance traveled would be 4, 8, 10, 12. Okay? Think about it like when you go out for a run, right? Maybe you're the moving man. And you just run back and forth in front of your house, okay, on your street. You never go around the block because that would imply 2 different variables, and we are in single variable calculus, okay? But your displacement, if you get back home, is 0, right? You're right back where you started, hopefully on your couch relaxing after a run. But you want credit for all of the running that you did. So given credit is the total distance traveled, where we don't care if you were moving to the right or to the left. It's not going to negate each other. Okay, we want to actually add up all of your distance traveled. So let's see what this looks like on a graph if we plot our distance, our position, x of t, versus the time that our running man was running. So our time, pull this back up, with our, go back, our play. So at 1.32 seconds, he's at about 4, back, etc. Okay? So I'm going to say 1, 2, 3, 4. So we go 1, 2, 3, 4 meters in the positive direction until about 2 seconds. Then we turn around and we go back in the negative direction, only back to -2, and then we got back to where we started, okay? So in thinking about this graph, right, we were moving to the right 4 meters, Then we move to the left 6 meters. Then we move back to the right 2 more meters, which is where our 12 is coming from, right? 4 plus 6 in the negative direction, back to where we started. So when we think about the slope of this graph, the slope, also known as the derivative in calculus, the slope of position would be the change in position over time, which those of you that are my physics people hopefully would tell me that that is equal to the velocity. It's the change in position over your change in time. Okay? Notice that our slopes are positive, then negative, then positive. So moving to the right, then we briefly turn around, we move to the left, we briefly turn around, and we're back to where we started. So where our slope is equal to 0, we have a turnaround spot. All right, again, where the slope of position is 0, we turn around. All right, so slope of position, change in position over time, this is just rewriting what I just had, is velocity. So if v of t is greater than 0, which I did in red this time, v of t is greater than 0, means v of t is positive, then position is increasing, which means that we are moving right, moving forward, moving in the positive direction, okay? It means that we have a positive slope on S of t, okay? If v of t, the slope on the position graph, is negative, that means that our position is decreasing, which means my running man was moving left, backward, in the negative direction. We see a negative slope on S of t, right? So S of t is decreasing. The last one then is what happens if v of t is perfectly equal to 0? Then the particle, or our motion, our man, right? The particle is at rest. There's a potential max or min, a potential turn, if you will. The reason I say potential is that we know we could have times where a slope is 0, but you don't actually turn around, right? So think about from a graph, we could be increasing, chill for a little bit, and then keep increasing. We do have a moment where our particle is at rest, but we didn't actually turn around. We didn't switch from going to the left, going to the right, vice versa, okay? If you think about it on a derivative number line, we wouldn't have had a change in signs. We would have just had a critical number, all right? Speed is the absolute value of v of t. Absolute value means that we're going to make everything, all of our velocities, positive. So speed is velocity without direction. And we'll look at that in a little bit. Velocity without direction. So you want to think about the fact that your speed, even if you're running to your left, right, your speed is still positive, but you would say your velocity is negative because you'd be moving to the left. All right, so slope of velocity then, slope in calculus meaning derivative, right? The derivative of velocity, you guys know my pen struggles. The derivative of velocity is the change in velocity over time, which is the acceleration. Change in velocity over change in time. I have here for you this nice little chart of ways that we notate things. So if we call position s of t, we would notate velocity as s prime, which means acceleration would be s double prime. We could also say that position is just called s, in which case velocity would be ds dt, and acceleration would be d squared s dt squared, the second derivative. Okay, well then even more so, another way we talk about velocity is v of t, in which case acceleration is v prime. And another way we can talk about acceleration is just a of t. So when we think about this, in terms of a list and order, position, take the derivative, you get velocity. Velocity, take the derivative, you get acceleration. So we're taking derivatives in this order. You can anticipate then that if we have acceleration, we could go backwards with the antiderivative to get the layer up above. All right, there are 4 different examples in your notes packet. This one is a position versus time graph. So I want you to think about the moving man. I did put the link to the moving man in today's folder, so if you want to use that for the position versus time graph, you can. Velocity is the next one. So notice this is now looking at velocity, which is like looking at a derivative graph, right? This is now looking at s prime. There's one that is a algebra problem, and there is one that is a multiple choice problem. So what I would like to have you do is go through and try each of these problems for yourself and write down your answers in pencil lightly, okay? And just think about it. Think about what we talked about. Think about creating the situation in your head. Picture the moving man, all the things that are happening. Think about your definitions. What does it mean to move to the right? Well, that means that we have a positive slope of s. Where do we have a positive slope? Where we see our function increasing, okay? Try them for yourself. Sorry, I'm rambling at this point. Try them for yourself and then watch the second video where I go through each one of these things, okay? But please, please, please try on your own and then check your understanding with the video.